Hey y'all! So we're going to start Chain Rule episode 2 today. We're going to revisit the chain rule, see some more examples, get better at it, and then go and work some actual problems. Not just the derivative, but use it in things. So this is Chain Rule episode 2. Just as a reminder, this is our rule if we have a composite function, f of g of x, and we have some function u, which is inside of here, we can use the notation that f prime of u times u prime is chain rule derivative of the whole function f of x. So there's these two ways to write it. F of, and you replace the whole function with u times u prime, or you can say f prime and keep the g of x times g prime of x. So both of these notations hopefully will start to make sense to you the more that you use them. So we're going to call this u substitution. So instead of writing the entire baby, if you will, the entire inside function, we're going to use the u substitution. So let's go through some examples together. Here's two examples. We have a equals cosine of x minus 1 and b y equals 2 times e to the 3x. I do want to use some u substitution today to get you a little bit more familiar with that. So if I have cosine of x minus 1, this is a composite function. This is the part that is composed inside of the cosine function. And so when I take the derivative, y prime is equal to the derivative of the outside, and I'm going to keep the u part. So I'm going to say the derivative of cosine is negative sine x minus, I write s, negative sine of x minus 1. This is the u part, times u prime, which is 1. So this was a very simple derivative because the inside function's derivative was 1. So this part is the u, it's the composite function, and we're going to multiply it by u prime. Same thing here. If I think of this as u, I'm going to say this is 2e to the u. And when I take the derivative, I'm going to take the derivative of e to the u and then multiply it by u prime. So I'm saying that u is equal to 3x in this case. So to do that, y prime, or I'm going to use the dy dx notation here, the derivative of y with respect to x here. So that's going to be, I'm going to keep this coefficient, we talked about that the other day. We're going to keep the 2, nothing happens with the 2. And then we're going to say the derivative of e to the 3x is e to the 3x. We keep the u. Derivative of e to the u is the same thing, e to the u, times, so this is e to the u prime, times u prime, and u prime is 3, which is going to be equal to 6e to the 3u, which is 3x, 3x. I'm going to keep doing u substitution so that becomes more and more familiar to you. It probably still seems a little bit weird and awkward right this second. Okay, so what else do we have? Let's do trig parentheses. So you've got this, hopefully, that you're working on notes for, so it's going a little bit faster than before. So I have these 5 different, very similar functions here. And I told you that I really dislike it when people don't put parentheses. So these are all very different, and let's put parentheses to make them really clear what they actually are. So in this first one, I'm going to use a different color. This first one, I'm going to say that this 3x squared, this is the composite part of the function, the g of x. Here, I'm going to say this is actually cosine of 3 times x squared. Now I'm going to do 3x squared. This last one, I'm not going to put parentheses. Well, I can put parentheses right here. But that's equal to a different idea of a function that I'm going to write differently in a minute. And then this is too. So D and E are very similar. So the derivatives for these are all different depending on where the parentheses go. I prefer that you go ahead and put parentheses with every function so that nobody has to guess what you mean, because they're going to guess this. If you don't put parentheses, this is the default. But this one and this one are very, very different. So when I take the derivative of a, I'm going to have y prime equals, this is a composite function. The outside function's cosine, so I'm going to do that first. Keep the baby times derivative of the baby. So I'm going to have derivative of cosine is negative sine. Keep the 3x squared times the derivative of 3x squared is 3 times 2, 6x to the first power. Better written as negative 6x sine of 3x squared. So that's the first one. The second one, let's think about that for a minute. Cosine of 3. Cosine of 3, is that a function or is that a number? So if you put cosine of 3 in a calculator, what do you get? So if it's a function, you're going to get a whole bunch of different inputs and outputs. If it's just a number, you're just going to get one thing. So cosine of 3 is actually just a number. It means if you said cosine and put 3 in, you get some decimal out. So this is a lot like the square root of 2. I don't know what the exact number is. It's not something on my unit circle. It's not pi or pi over 6 or something that I know from the unit circle. So I'm going to leave this as cosine 3 just like I did up here with the 2. I'm going to consider this the coefficient. So this turns into not a composite function at all. This is the coefficient. This is going to be y prime equals, keep cosine of 3 times the derivative of x squared, which is 2x. And this you'd have to evaluate cosine of 3 times 2 to get a decimal if you wanted to write it a different way. So that's a crazy looking 3. Let me make it better. Cosine of 3. So that's just a number. Surprise! Then this next one, cosine of 3x squared, that really means that this 3x is squared. Maybe even parentheses should go like this. It's not x squared, it's the whole thing squared. So this is actually equivalent to cosine of 9x squared. And so when I take that derivative, similar to the first one, I'm going to say y prime is equal to, derivative of cosine is negative sine, keep the composite part, times the derivative of 9x squared will be 9 times 2 is 18x, or negative 18x times sine of 9x squared. Sorry for the giant shadow. Okay. Cosine squared x. That's a different problem entirely. It's composite, but in a different way. This is equivalent to, and for derivative purposes, it's much easier to write it this way. The entire cosine function is squared. Not x, but the entire cosine function, which means that now this is not the parent function, this is the baby part. The outside function, the mama function, is the squared. So first we're going to do power rule, keep the baby, times derivative of the baby. So y prime is equal to 2, keep the baby, cosine of x, to the first power, because we reduce, times derivative of cosine of x, so negative sine of x. So the derivative y prime is equal to negative 2, negative 1 times 2, negative 2, and then cosine times sine. Cosine of x, sine of x. And then e is very similar, so it's going to be cosine of x to the 1/2 power, which is just the power rule. So we're going to use power rule and then keep the baby and derivative of the baby again. So it'll look very similar, except I'm going to have something in the denominator when I do this one. So I've got room for this one. Y prime equals power rule first. It's something to the 1/2 power. So 1/2 cosine of x to the negative 1/2 power times the derivative of cosine is negative sine. Parentheses are also important here because otherwise it would look like a subtraction problem, and this is multiplication. So if I'm going to rewrite this really pretty, I'm going to say y prime equals 2 goes on the bottom, cosine of x goes on the bottom, negative sine of x is on the top. So negative sine x to the square root of cosine of x. There's the square root there. So parentheses are really important. They're one of my pet peeves, but the book does a good job of going through these examples, so you can go through those if you have questions as well. Okay, so page 2 says, here we go with the chain rule and Star Trek Tribble. So I don't know if anybody looked these up. I'm going to give one of the Gerber girls a shout out for thinking about this a couple years ago. So what happens when you've got multiple chain rules happening? So you've got multiple gears going on. And if we use the example of the mama and the baby, which is my favorite, then what happens when the mama's got a baby and the baby's pregnant with the baby and then pregnant with the baby and there's so many babies? So here you go, in case you didn't look it up. Here's Star Trek Tribbles.
Yes, sir. Good. Open it. Not working, sir. Please restart.
Okay, sorry, that was a terrible recording, but I forgot to make it so you could hear things on the recording from the computer, so I had to go another route. Anyway, so those are tribbles. So they just multiply, 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 and that's what death by chain rule is. So instead of thinking of death by chain rule, we're going to think of happy little fuzzy tribbles when we look at problems like A. F of t equals sine cubed of 4t. This has 3 layers to it. It has, let's write it as sine of 4t all cubed. So there's 3 things going on, 3 gears to this problem. The outside gear is the something cubed. The inside gear is sine, and its inside gear is 4t. So we have 3 layers to this. We're going to take the layer of each one and keep the baby, and then take the derivative of that baby, and then take the derivative of that baby. So here we go. F prime of t equals, I'm going to take the derivative of something cubed first. So I'm going to say 3 times the baby to the second power. 3 sine of 4t to the second power times sine of 4t prime. That's the derivative of the baby. I haven't taken the derivative of this part yet, but I'm telling myself I'm going to by putting a prime on there. So it's the beginning of chain rule, death by chain rule. This is how you survive it. You do it one piece at a time. So I'm still doing the derivative. I've got 3 sine squared of 4t. I'm going to rewrite that all pretty now. Now I'm going to take the derivative here. Now I have chain rule again. I have sine as the outside function, and its composite is 4t. Its gear is 4t. So the derivative of sine is, this is all multiplication, cosine, keep the baby, times the baby prime. And I know you could do that in your head, but I'm trying to keep a rhythm here. So now I have f prime of t equals 3 sine squared of 4t times cosine of 4t times the derivative of 4t is 4. And altogether, that will be f prime of t equals 3 times 4 is 12 sine squared, of 4t cosine of 4t. So this was 3-layered. Mama, baby, and baby again. Let's try B. B has also got 3 layers to it. The outside function is secant. I'm going to take the derivative of secant and keep the baby. I'm going to take the derivative of e to the 4x and keep the baby. And I'm going to take the derivative of 4x. I'm going to write it out like I did the last one. So g prime of x is derivative of secant is secant tangent. So secant of keep the baby, tangent keep the baby, times e to the 4x. I need to take that derivative. So it's derivative of the outside function, keep the baby, keep its part that was the gear inside, then take the derivative of the gear. So I'm working this little by little. I'm going to keep secant of e to the 4x, tangent e to the 4x, and I'm going to take e to the 4x prime. E to the 4x is just itself, e to the 4x times the derivative of 4x, which is 4. To make this the prettiest thing I could, I would end with g prime of x. And normally we put the 4 in the very front as the coefficient, and then we end with trig. So we'd say 4e to the 4x, and then secant of e to the 4x, tangent of e to the 4x. And that's remembering this rule that d dx of secant equals secant x tangent x. So whatever is in here stays when you take the derivative. All right, so this is death by chain rule, and y'all are surviving it. I feel sure, but I also feel sure that y'all will ask me if you have questions. So another 3-layered one. This is outside function is the square root. Inside is sine, but sine has its own baby as well. So many of you will do better if you keep the sine of e to the negative x plus 3, but then you put the whole thing in as to that 1/2 power. And what that does is when it's written like this, you recognize it as power rule. It's going to be whatever is inside of here is power rule, so 1/2 goes to the front. Keep the part where my fingers are, and then subtract 1 from here, so we get negative 1/2. Then we're going to take the derivative of the inside. So h prime of x equals 1/2 sine of e to the negative x plus 3. That stayed the same to the negative 1/2. So that's power rule on the entire thing times this whole piece, the baby, sine of e to the negative 4x, sine of e to the negative x plus 3 prime. Again, this is a middle step that some of you can skip, and you know who you are. But in order to not be killed by chain rule, it is good to take it one step at a time. So this is the outside function, and you can now see that you've got u prime. If you want to look at that first set of instructions that we saw before, this would be f prime of u, keep the baby, times u prime. And then we're going to do that again. So next step is still going to be the derivative. I'm still going to keep it just like this for now. Sine of e to the negative x plus 3. And now I'm going to take the derivative here. I'm going to take the derivative of the mama function. Sine is going to be cosine, keep the baby, times derivative of the baby. So at this point, I think I can take the derivative of this part. I'm going to have, oh, it's got another baby. E to the negative x, keep the baby, times, I'm going to keep my same notation. I'm going to go back. So I've got sine is cosine, keep the baby, times the baby prime. And I'm going to do that next. H prime of x equals 1/2 sine e to the negative x plus 3 cosine e to the negative x plus 3. And when I take this derivative, I'm going to take e to the negative x stays, e, that's its composite function. Now I have to take the derivative of this, which I am going to go ahead and do, and that's -1. So this was a 4-layered one. I was wrong. Square root sine e had its own composite function. If I rewrite this all pretty and neat, oh, I lost the -1/2. I know y'all were telling me that the whole time. I just couldn't hear you because I'm on video. But here you go. Here's the -1/2 all the way there. Sine's derivative is cosine. Keep the baby. This derivative is the same times -1. Okay, I've got all my pieces. I'm going to rewrite it. I'm going to put this and this in the denominator. I'm going to leave all of this in the numerator. And I'm going to write it as -1 e to the negative x cosine of e to the negative x plus 3 all over 2 and the square root of sine of e to the negative x plus 3. Okay, that was wow. That makes you want to think of little fluffy tribbles because it's kind of crazy town. But this is why it's called death by chain rule, is because it can go on and on and on. But each of these are gears that turn and they affect the derivative. Okay, we're switching gears slightly. We're going to see one more function that we're going to take the derivative of. And I've already written this out for you. So far we have seen derivatives of algebraic functions and transcendental functions. So algebraic functions would be like x to the 4th or the square root of x squared. That's just x. The square root of 4x plus 2x plus whatever with composite rules. So algebraic functions like polynomial functions and square root functions. And then transcendental functions, we've learned e to the x, sine, cosine, all the other trig functions. So normally, algebraic functions have algebraic derivatives. Transcendental have transcendental derivatives. But the natural log function is different. It is transcendental, meaning it's not a polynomial algebraic function, but it has an algebraic derivative. So it's a combination of the two. So they've saved this for the chain rule chapter. So let's look at, we don't know the derivative for natural log yet. Let's consider y equals the natural log of x. If you recall, the natural log of x has a vertical asymptote at x equals 0. It follows the asymptote down like this forever, and then it kind of goes up like this. It looks a little bit like the square root function up at the top. This is the 0.10 for the plain natural log function. And the domain here is 0 to infinity, not including 0, because that's an asymptote right here. All right, so if we're thinking about what its derivative is, let's go and actually figure out what the derivative is. In other words, let's look at the picture of it. And I'm using green. You can't see green very well, but maybe enough to sort of, as I write on this. If you would describe the tangent line right here, it's very light probably in your drawing, but it's very, very steep. It's a high number. Like it would be up 1,000 over 1. It's a very large number. So we're going to call this m equals, let's just say 1,000. That doesn't show up very well, but it's 1,000. Right here at the slope, this is pretty much a 45-degree angle. Pretend my drawing is immaculate and beautiful. Then we're going to say at 1, slope is 1. It's up 1 over 1. And then as we go over here, it starts to be a smaller number. So it's like up 1 over 10 or something. So we're going to call this, we'll call it 10. I'm making these up. I'm just trying to give you some understanding of what the derivative is going to look like. If we go and we use these numbers and we try to graph the derivative, so we're going to graph, I'm just going to call it natural log prime. So natural log of x prime, that notation that I used before. If I try to graph the derivative at this very close, so before 1, this very, very small x value, I'm at 1,000. Okay, so I'm really high. This is not to scale at all because this is like 1, 1. And at 1, I have slope 1. And up 1 over 10, that's not 10, that's 1 over 10. Up 1 over 10 is up 1 and over 10. It's 1/10. So that means way over here, so I don't know where I am. I'm about this far away. My slope is 1/10. It's right here. And if I graph this and connect it, it's going to look like this. Considering that the domain for this is 0 to infinity, there is a function that you know that looks like this if we just consider this domain. And it turns out that if y equals the natural log of x, then y prime actually equals 1 over x. One over whatever the composite part is. So in this case, it's just x, 1 over x. If you remember, if I was to graph all of 1 over x, it would also be over here, right? But I can only consider 0 to infinity. The derivative carries over the same domain. The domain of the original function. So its domain, even though it's 1 over x, it's not everywhere except for 0. It's only going to be from 0 to infinity, the same domain as the natural log function. So the derivative carries over the domain of the original function. And that's true for all graphs. If your original graph only goes to so many numbers, then the derivative will go to those same numbers. So we have a new rule. And the new rule is, I'll write it again. I'll write it in a dark pen so you can see it. If y equals the natural log of x, then y prime equals 1 over x. And we're going to add that to the things that we memorize, like sine and cosine, tangent, secant, all of those. We're going to memorize this just like e to the x. All right? So let's use that here because it's handy when we get to composite functions, because natural log is not always just natural log of x. It's normally something that's been shifted. This is a composite of x squared. This is a composite of sine of t. This is a composite of x squared minus 9. So these various functions will have different domains as well. So in these 4 examples, I've got 3 different notations for you to recognize for the derivative. I've got Instead of y prime here, I've got the derivative of y with respect to x. And what that means is we're going to take the derivative of the outside function, which is 1 over whatever's in here. So 1 over x plus 2, that's this derivative, but in a composite form, times the derivative of x plus 2, which in this case is just 1. So we end up getting dy dx just equals 1 over x plus 2 for A. The derivative, oh, I didn't write the derivative notation. I said it, but I didn't do it. So its derivative is just 1, and so we get 1 over x plus 2 times 1. Going on to B. I have a composite function again, the natural log of x squared. So this time I've got the notation y prime. You could have just as easily written dy dx. So the derivative of natural log function is 1 over whatever's this gear is inside, 1 over x squared times the derivative of the baby. So the derivative of the baby is 2x, and we're going to simplify that to be 2x over x squared. So y prime really simplifies to 2 over x. And that will happen a lot with the natural log function. Once you take the derivative and multiply it, it goes on the top, and then usually a lot of times things cancel. Hopefully you're starting to get the hang of how the composite works with natural log and the new derivative that we've got. This one I put a t in here just so you're familiar with changing of variables. Natural log of sine of t, that's another composite function. This is the outside function. This is the inside function. Derivative of natural log is 1 over sine of t times the derivative of the baby. So that's going to be cosine of t. So dy dt equals cosine of t over sine of t. I'm getting all my parentheses in there. And that's actually simplified to cotangent of t. Our last one, not that much more complicated than anything else we've done. Y equals this. Y prime is going to be 1 over x squared minus 9 times derivative of that is 2x. So y prime equals 2x over x squared minus 9. No simplification needed for that one. So a new function, put that in what you have to remember. And there's a great chart in this section that we'll look at together just to confirm all the different ones that you know already. And it also talks about logarithms with different bases. We'll look at that at another time. All right, next I want to talk about properties of logarithms. We're going to recall that real quick before we take some derivatives. If we remember those properties, it will help us simplify things so we can take derivatives easier. Let's rewrite this. F of x equals the natural log of the square root of x plus 1. So this is not in your notes. You just need to start your own notes at this point. I'm going to rewrite this as the natural log of x plus 1 to the 1/2 power. And then if you remember your logarithm rules, when you have a log with an exponent, exponents are multiplication within exponents. So this is the same as 1/2 the natural log of x plus 1, which is a way easier function to take the derivative of. So we're going to take the derivative now of our simplified version here. We're going to keep the 1/2 because it's a constant in the front, 1/2. We're going to take the derivative of natural log. We do 1 over whatever the argument is, so times 1 over x plus 1 times the derivative of this argument, which is 1, and we get 1 over 2x plus 1. A way easier derivative to take than if we'd have left it in the square root. Let's do another. This one looks really gnarly, and it probably is gnarly, but it'll be better when we rewrite it. So B is the natural log, and this is a fraction. So we've got x squared plus 1 squared over the square root of 2x cubed minus 1. So this is the entire argument for the natural log. So let's think about our rules. We have powers here, we have multiplication, and we have division. So we have those three things that we're going to rewrite our logarithm. And I don't have a y equals, but pretend that it said y equals there. Let's rewrite this as y equals, because I don't need the equals there, go and look crazy. I'm going to rewrite one more thing. I'm going to say the natural log of x times x squared plus 1 squared over 2x cubed minus 1 to the 1/2. And now I have multiplication, multiplication, division, and some exponents. So I haven't done any derivatives yet. I'm just rewriting those logarithms. I'm going to have y equals, but y'all, quotient rule with this, and product rule on the top, and chain rule, I mean, this is death right here. So let's rewrite it so it's easier. So logarithm properties mean that since they're exponents, we can use exponent rules. When we see multiplication with exponents, that means addition between the exponents. So we're going to separate them and say the natural log of this piece. Remember, things on top get a plus, so it's a plus in the front, a plus right here. We're going to separate this into the natural log of x squared plus 1 squared. Things on the bottom get a minus sign, natural log of 2x cubed minus 1 to the 1/2 power. So those are properties of logarithms that we did in definitely last year in pre-calculus. We might have hit it just a little bit at the end of the year in Algebra 2. And we can do one more step here. We could put this 2 in the front, and we could put this 1/2 in the front. So since logarithms are exponents, we think about those rules with how exponents work. So when you have the same base, you add the exponents, and then you subtract if that's division. When you divide, you subtract, and when you multiply, you add. So anyway, we're going to now take the derivative of each piece. We have this piece to take a derivative of, 1 over x. We have this piece to take a derivative of, it's going to be 1, I'm thinking ahead, sorry. It's going to be keep the 2. The natural log the natural log derivative is 1 over x squared plus 1, and I got rid of this 2, times, so 1 over the argument times the derivative of the argument, minus, keep the 1/2, the derivative of the natural log part is 1 over 2x cubed minus 1 times the derivative of its argument, which is 6x squared. So each of these pieces has its own derivative, and this is too messy. We're going to neat it up a little bit. We have 4x in the numerator on this one, and x squared plus 1 in the denominator. We have 6x squared and 2 times 2x cubed minus 1 in the denominator. I should have written 3 there. So I had 6 divided by 2 is 3x squared. And this is the derivative without having to do bottom derivative of the top, which would have been product rule and chain rule. That would have been a disaster. So natural log, properties of exponent rules, property of logarithm rules, have to go back and remember those lovely rules. Okay, so your homework is posted on Google Classroom, and due dates are posted there. So do your very best. They're mainly derivatives with using the chain rule. Some of them I think are actually second derivatives, and then there are a couple where you have to find actual slope. So you find the derivative and then you plug in the x value to find the slope. They do want you to check some on the calculator and practice that. So if those give you any trouble, make sure you circle them so we can go over them next class. All right, thank you.